Going to start here. Hello, my fellow fellows. So today, yeah, Anthony, I hope it's okay if I go. So today I'm going to talk about the UniFormer, which was developed by Lee et al. In this recent archive paper. So first of all, let's talk about what the motivation is. Also, can everybody hear me? I just want to make sure.
Yes, Alex, you're audible.
Thank you. Okay. So yeah, the video understanding is a tricky problem because you have very redundant information for local frames and in the spatial information of local frames. But you also have to keep track of these long-term dynamics, especially in disambiguating certain actions and understanding the video. So these nearby frames contain really redundant information in these subtle motions, and that increases with the sampled frames per second. So if you sample extremely densely, you essentially just get more of this dude just standing here. So these are frames from the activity recognition data set. And in this context, if you just look for short range between the short range frames, the model might estimate that this guy is just standing here. But as you go to longer range frames from 1 to 30 and 60, you can see these longer term dynamics in terms of the spatial and temporal dynamics here. But at this point, it's still unclear in this video, is this dude cheering or dancing? He could just be raising his hands up and just, cheering for a team or whatever. But when you increase even longer range actions and continue on the temporal dynamics, you can disambiguate certain actions better. And including that global context is a really important piece. And then at this point, you can tell that this guy's changing motions and he's just dancing. So that's the challenge here, is to efficiently compress all of this local redundant information from frame to frame, so efficient processing of videos, while also capturing these long-term dynamics to disambiguate and identify particular actions. So this is the motivation in which they designed their model. So let's talk about previous models first. So most previous approaches focus on efficiently capturing the local spatiotemporal information or the global spatiotemporal information. So 3D convolutions are great and particularly state-of-the-art for the 3D local learning and are very parameter efficient. But they're not very good at learning the long-range dependencies in videos and distinguishing actions based upon long-range changes or these temporal changes from one frame that's very far from another frame. But in contrast, these recurrent neural networks, or LSTMs, and transformers that have the recurrent or residual components and capture longer range dependencies with global attention mechanisms, can do the opposite. They can learn these long range dependencies, but they suffer from being very computationally costly and wasteful. So to sort of drive home that point, the authors utilize this time S-former, which is a typical video transformer model, and they apply it to the kinetics dataset. And here you can see these green tokens are the anchor tokens, and they're actually compared to all frames for the spatial attention. They're compared to all frames in, all tokens in the frame. But the activations here, denoted by the intensity of the red, only really pays attention to local information. So this is just from a learned parameter that essentially just focuses primarily on local features. So even though it's only essentially doing significantly 5 operations here, it's doing however many token operations there are in the frame. So it's very inefficient for just paying attention to local information. Likewise, for the temporal attention, it will take this anchor token, compare it to all tokens in that same spatial location across all times in the frame. That's obviously also very inefficient, especially depending on how many frames there are and where you put the threshold for the comparisons. but it only, again, pays attention to this local information of the previous frame. So also, everybody feel free to ask questions whenever you want. Definitely just a casual thing here. So, so the authors, to tackle this difficulty, they define or come up with a model called the unified transformer. And the idea here is to combine the strengths of 3D convolution and transformers in a concise and unified module and model. So interestingly, the spatial and temporal components are treated equivalently here, and that's not always the case in these video understanding models. Furthermore, the authors designed their own multi-head attention formula for unifying your 3D convolutions and spatio-temporal self-attention. And each of these MHRAs is what they're called, multi-head relation aggregators, have local and global forms. And the local form more or less uses the strengths of 3D convolutions, while the global form has the transformer strengths and more global feature attention. So the affinity, value, and norm functions that define these MHRAs are uniquely defined for the local form of the MHRA and the global form of the MHRA. And affinity is essentially this covariance matrix that modulates the input attention and compares the tokens based on different formulae, either globally or locally, again, for the local versus global versions. So these UniFormer blocks are then essentially staged. So in the shallower layers, they use this local MHRA UniFormer block form, and it efficiently captures and learns and reduces the parameterization of these locally redundant regions and the redundant frames, redundant information in nearby frames. And then in later, deeper layers, the global MHRA is used for learning longer range dependencies in the video. So that's all like kind of a vague summary of the approaches, but to go into more detail, this is the UniFormer block, which is the main contribution of the authors. So first of all, it starts with this dynamic position embedding. So really what it is in this paper is a 3D depthwise convolution. And it efficiently encodes the redundant spatiotemporal information in local frames. And importantly, this dynamic positional embedding is used in other transformer models as well. And the main feature of this, of the dynamic position embedding, is that it essentially recovers or keeps the same sequence for the spatiotemporal input. It allows the model to learn from the sequence ordering, which is extremely important, of course, for the transformer and global models and global attention in later layers. And on that note, you can also note here that these residuals actually transfer an unaltered version of the input all the way to the output layer. So even if you apply these local MHRAs first, it doesn't get rid of the information present in your input. And that's particularly important for later global relation learning. So the second step here is these multi-head relation aggregators, MHRAs, which I talked about briefly earlier. So they concatenate the tokens and they weight them by this token affinity function and this value function. And then they're concatenated and depend upon this learnable parameter U that essentially weights them differently. And these have different forms, and I'll talk about these functions later when I talk about the forms that the MHRA takes. So the final piece here is a feed-forward neural network that combines all of these resulting tokens and can do point-wise enhancement for improved classification accuracy. Yeah, and as I said, there's these residual components that sort of last through. And to drive home this point and sort of, I like looking at the math of how the operation is done. So the first step here is this depthwise convolution of the input. So it's this set of coupled equations, 3 coupled equations here. You first just take the input depthwise, add its residual, You reshape it, then you apply these MHRA functions with pre-normalization to that resulting output. And then you finally feed that to the feed-forward neural network. And the feed-forward neural network is just simply a linear, two linear layers with a Gaussian error linear unit activation function intertwined here. So the full formula, when you plug all of these, when you essentially solve for the output in terms of the input, has this full form here. So as you can see, the final output is directly related to the initial input without any sort of transformations, which again is passing on this unaltered information for future layers, which is a very important part of the design. Otherwise, it applies this feed-forward neural network to all of the other transformed steps here and transformed features. In this R vector, the relation aggregator is essentially just the concatenation of multiple heads. That's why it's called a multi-head, multi-head relation aggregator. And each of these are relations. And yeah, they combine and then are weighted by this learnable parameter matrix U. It's linear. And each of these relations are weighted by this affinity function, which again relates different tokens based on some function you define, and that's defined uniquely for the global and local MHRAs, and also this value function. So in more detail on that, going to the local MHRA, here we have the affinity function. So the affinity function compares, this is the, this is the anchor token denoted by I here. And this is the comparison token denoted by xj. So you compare the tokens, and however far the jth token is in terms of spatiotemporal distance, so it can be either frame distance or spatial distance, it essentially decays exponentially with that distance and is zero otherwise if it does not fit into this tube. And you essentially, the users get to define the size of this tube, this TH, time, height, and width. And furthermore, the authors also use this pointwise convolution for the value function. So the value function can be any sort of linear transformation that maps the input to a set of relation tokens. And then the normalization that they use before applying the pointwise convolution and everything in the rest of the steps in the MHRA. So this is just the normalization first applied to the X input, is this batch normalization form. And this is just the mean of the batch, and this is the standard deviation of it. So the local MHRA actually can be understood as just sets of cascaded sets of convolutions. So first you start with this pointwise, then depthwise, then pointwise convolution. And that's essentially the same application as this model. So it's essentially just, using the strengths of convolution because it is essentially a convolution. So global, as for the global MHRA, the affinity function here, again, this is the anchor token. These are the comparison tokens, is actually global. So you can see here, this form is really similar to the Boltzmann equation. So it's just for a given set of tokens for a single pair, you weight them and then you divide them by the total normalization, the total value of all of the weights of each of these tokens over the full input. And furthermore, it follows a pretty standard definition of the transformer query, key, and value functions, which are just related from the original input by this, again, learnable parameter here, lambda. I believe it's learnable. And yeah, they're just a linear transformation that you can use. And then the normalization is a layer normalization that this is the mean of the full input, and you essentially use the full input. So again, the themes here are, batch and local, and then, global and universal here. So you can see that they sort of keep that consistent, and it works consistently and well. And the full global MHRA is essentially just a spatiotemporal transformer. So it's just definitely just a transformer, and that's why it has the strengths of the transformer. So the full model actually uses stages of these UniFormer blocks. So each of these stages consists of multiple applications of the blocks. So starting from the beginning here, you put in your input videos, you apply the strided convolution, which essentially downsamples the video sum, and then you feed that into this stage, which has multiple UniFormer blocks applied. And like I said earlier, the first two stages, the shallower stages, are local MHRAs, while the later stages are global MHRAs. So that breaking it up also helps first reduce redundancy and then focus on global information for a good combination of efficiency, but also temporal dynamics attention. So in the UniFormer S, there's 3 of the UniFormers applied, then 4, then 8, then 3, and by UniFormer, I mean UniFormer blocks. And then the UniFormer B applies 5, 8, etc. So yeah, the model finally ends with some average pooling and a fully connected layer for the final classification of the video. So the experiments focused on activity recognition tasks, which is highly relevant to the fitness activity recognition project track, which I'm on with some great coworkers here. And the model is pre-trained on ImageNet 1K, and then it can actually classify these kinetics and something videos. The kinetics have 400 different action classes or 600 different action classes in their shorter term, while the something have about 170 to 200 classes for action classes, and they're more like long term. So there's just like daily life activities, and then the model has to label those long term activities, and they're just not as sort of dramatic or dynamic and sharp as the kinetics. So the authors also inflate the pre-trained ImageNet kernels for the kinetics data set, just matching the dimensions and making it efficient. And then they use dense sampling for the kinetics as it's shorter term, and uniform sampling for the something as it's this longer range dynamics here. And then they use an Atom W optimizer and cosine learning rate with some warm-up hitbox and whatnot denoted here. So in terms of performance, the UniFormer actually achieves state-of-the-art on the something version 1 and version 2. And they improve the top 1% accuracy of the something version 1 and version 2 data sets by 4.2% and 1.6% in the top 1% accuracy. So, add a couple extra little digits there, but, still impressive increase in performance or accuracy. And importantly, they also require a lot less flops per video than these other comparable state-of-the-art methods. So as you can see here, theirs is the pink stars. And yeah, it's pretty impressive how little flops per video it requires for how accurate it gets. And that's really cool, and part of that is their design. Furthermore, it can also be used as the backbone of certain pose estimation models, such as pose. And this gets skeleton key points of the body, and they can be used as features to input into a later action classification model, which is essentially what we're doing with MoveNet, or what the previous cohort had done with MoveNet in action activity recognition. And of course, this is just their example video, but which is beyond our scope of having multiple people, but we would reduce it to just one and it would still work fine. So ablation studies, these essentially are trying to figure out which pieces were really important for the effective functioning of the model. So the authors find that this joint spatiotemporal learning increases accuracy and efficiency of the transfer learning. And then the MRHAs have that extra feed-forward neural network that really boosts classification accuracy, and they compare it to a model which does not have that, but is similar otherwise. And very importantly, the combination of local and global MHRAs allow the model to discriminate actions based on both spatial understanding and long-range temporal understanding. So for example, gargling apparently is difficult for a completely global attention or transformer model because it tries to focus on more long-range attention and more global diffuse attention, and doesn't focus as much or as well on relevant features for gargling as the completely spatial convolutional set. So LLL implies that the UniFormer blocks applied are all local, 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 or local, local, global, global, or global, 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 global. So yeah, the gargling, its closest companion, like estimated action, is brushing teeth. But the spatial understanding of the transformer or of the convolutional based local MHRA does a great job of distinguishing these two because, hey, there's no toothbrush, so I guess it must be gargling, even though it somehow looks similar. Or another example the authors use is swing dancing. It's harder for it to discriminate. And oppositely, this playing guitar versus strumming guitar, it's very important for the model to focus more on the longer term dynamics because playing and strumming guitar can't really be easily separated by just looking at the spatial components of a certain frame. So this longer term dynamics learned by the global, global, global does a better job of distinguishing this kind of action. But importantly, this local, local, global, global does a great job at classifying both sets of them. So it's a combination that reduces computational cost because this global, 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 global is more costly in terms of computational resources. And it also achieves a very good discrimination of actions for spatial and temporal components. So to further drive home this point, that you have the local, local, global, global attention here versus the local and totally global. So as you can see here, the local attention does a decent job of finding certain relevant pieces, but can have fairly diffuse attention here and sort of focuses on sort of the wrong spot a little bit. Likewise, the global attention, while it initially focuses on some relevant pieces with kind of low attention magnitude, it eventually just compares things, has attention that is sort of global and diffuse, and it doesn't really focus on the relevant features here, the hoverboard. So hoverboarding is the action that the model is supposed to classify here. Meanwhile, this local, local, global, global does a great job of identifying the region of interest, which is mainly this hoverboard and the relevant feature here. So yeah, the authors design this very efficient and highly accurate video understanding model, and also works on ImageNet as well, and just like general image understanding. It still performs very well there as well. It's a very dynamic and it's a model that can be used for lots of different applications. So it relies on this UniFormer module, which utilizes spatial learning strengths of 3D convolution with this local MHRA block and the dynamic and global learning strengths of transformers via the global MHRA block. And using a combination of these types of blocks results in attention mechanisms that can focus on relevant pieces of the video frames, such as the hoverboard there, or like a football, and it can distinguish actions with both spatial, local spatial, and long-range temporal dependencies very well. It's quite impressive. And this joint spatial temporal learning, I really liked that aspect of this too. It improves both accuracy and transferability, and not treating time as a special dimension is, it is a special dimension in reality and in physics, but I like the symmetry of that. It is just another dimension at all. after all. So yeah, any questions? All right, well, if there are no more questions, I guess. Oh.
Hello.
You're welcome.
I was also going to present on the same paper. I did a brief presentation. It's not quite as detailed, but it's something. Yeah. This is it. So my name is Anthony. I also did a presentation on the same paper. So one of the challenges in learning rich and multi-scale semantics from high-dimensional videos due to large redundancies and complex global global dependencies between video frames. So this is really a challenge. And in recent years, the research has been mainly driven by 3D convolutional neural networks and vision transformers. As part-tuned temporal model arises when data is collected across time as well as space and has at least one spatial and one temporal property. So as much as yes, 3D has advantages such as it efficiently aggregates local context to suppress local redundancy from a small 3D neighborhood, it also has limitations such that it lacks the capability to capture global dependencies because of the limited receptive field. And then also the research advances towards vision transformers. Vision transformers actually are very effective to capture long-range dependencies by self-attention mechanism. But alongside this advantage, it also has the limitation of reducing local redundancy with blind similarities, with blind similarity comparison among all the tokens in each layer. So there was a proposal to come up with a novel unified transformer or a UniFormer, where the objective was actually to seamlessly integrate the merits of 3D convolutional spatiotemporal self-attention in a concise transformer format. So their main goal while doing this was to achieve a preferable balance between computational and accuracy. So let's look at this case study by it's a time-S transformer. So you have input frames from a video. I think this is someone on a hoverboard. And then you have the layer 3, which is the output feature. And then it also has the spatial attention and the temporal attention. So from our observation, it is very clear that such a transformer learns local representation with redundancy, with redundant global attention. And from this, you can see that the video wastes a lot of, there's large wastage on computational power to encode only very local spatio-temporal representation. So from this figure, we can clearly identify that the transformer learns detailed video representations in early layers. And then the spatial attention mainly focuses on the neighbor tokens, and the temporal attention mostly aggregates the tokens in the adjacent frames. While doing so, it ignores the rest of the distance frames. So this is the effect it has on the accuracy. So this is the accuracy of the per video GF loops. I think Alex has really explained this in detail. So from this, the local representation learned from the global token to token similarity comparison in all layers. Thus requires a large computational cost, which deteriorates, as you can see, it deteriorates the computational accuracy balance of such a video transformer. So this is the overview of the UniFormer block. It has 3 models or modules. One is the dynamic position embedding, the DPE, this. And then the next is the multi-head relational aggregation, the MHRA, which is the main focus of, I think, this study, based on the formulas presented to you by Alex. And then finally is the feed-forward network, or the FNN. So what this actually does is it tries to integrate the merits of a 3D convolutional and spontaneous self-attention in a concise transformer format. Hence, the transformer tries to achieve the best balance between accuracy and computation on the dataset. So like I've said, the modules, and then in a nutshell, this is how it operates. First, you introduce the DPE to a dynamically integrated 3D position. The reason to do this is to get information into all the tokens, which effectively make use of spatiotemporal orders of the tokens for visual modeling. And then after this, you leverage on the MHRA, which I think Alex has clearly detailed the formula to this, and aggregates each token with its contextual tokens, different from the regular multi-head self-attention. This tackles the local redundancy and the global video dependency by the flexible designs of the token affinity. And then finally, you add the FNN with 2 layers for pointers enhancement of each token. So on the ablation studies, does this style transformer help? So after investigating its effectiveness by replacing the UniFormer block in the shallow mobile nets with blocks, the default UniFormer outperforms such as spatiotemporal mobile net block. And then the FNN in the UniFormer can further mix the token context at each spatiotemporal position, just to enhance or boost the classification accuracy. And then another part of the study is the UniFormer versus the transformer. Is joint or divided spatiotemporal attention better? So clearly from the research, it demonstrates that joint learning is preferable for video representation learning. I think this was clearly illustrated by Alex in the video. And then in terms of the dynamic positioning, the UniFormer improves the top 1 accuracy. I think Alex illustrated this by 0.5% and 1.7% of the ImageNet and the Kinetics 400. Hence, while encoding the position information, the DPE can maintain the spatial temporal order, contributing to better spatial temporal representation and learning. So in conclusion, they propose the novel UniFormer, which is effective to unify 3D and convolutional spatial temporal self-attention, which is an improvement to the 3D and the VT. And then adopt a local MHRA in shallow layers. The reason to do this is largely to reduce the computational burden, and the global MHRA in deep layers, mainly to learn the global token relation. And then extensive experiments on this to achieve preferable accuracies between, to achieve preferable balance between the accuracy and the efficiency on popular video benchmarks. For example, the kinetic 400, 600, and something V1, V2. This work was done by the following people, and I've come to the end of the presentation. Any question?